All right, in today's lecture, we're going to cover the first part of the section 5.3 material on the integral test. So let's take a look at what the integral test says. So it says, suppose that the general term of our series, a sub n, is given by a function f of n, where f is a positive, continuous, and decreasing function on the interval from 1 to infinity. Then the series, taking the sum from 1 to infinity of a sub n, will be converging if and only if the improper integral of the function f of x, which defines the general term of my series, evaluated on the same interval from 1 to infinity, that is the same interval that I was taking my summation over, also converges. So what the integral test says is if the general term of our series, a sub n, can be thought of as a positive, continuous, and decreasing function over the interval over which we're summing, then that series will converge if and only if this improper integral converges. And if that improper integral diverges, then the series also diverges. So let's look at some examples where we may have to make use of the integral test. So in this next example, we're given a series and we're asked to determine when it converges or diverges. And in part A, we have the sum from n equals 0 to infinity of n times e to the negative n squared. Now, usually for a series, the first test that we want to try is the test for divergence, because that's the easiest test to apply. And as we're going to see, this test, this new integral test, can be a bit difficult to apply, so we usually want to save that integral test as a last resort to determine convergence or divergence. So here let's start by trying the test for divergence, which says that we would take the limit as n approaches infinity of this general term of our series, n times e to the negative n squared, which can be rewritten as n divided by e to the n squared power. So here, as n becomes infinitely large, we have a limit of the form infinity over infinity. So we can apply L'Hopital's rule to evaluate it. So we're looking at the limit as n approaches infinity. The derivative of our numerator is 1. And the derivative of our denominator is e to the n squared times the derivative of n squared, which is 2n. And now as n becomes larger, this ratio is approaching 0. So here, the test for divergence doesn't give us any information. Remember, the test for divergence says, well, if this limit is anything other than 0, we know that the series diverges. However, just because this limit is 0 does not necessarily mean the series converges. So here we find that the test for divergence fails. We get no result about convergence or divergence by applying that test. So we have to think of a new test to use. And so far, the only tests which we have are the geometric series test. And we can tell by looking at this general term that it is not a geometric series. It doesn't have the form a times r to the n. And we have a way to determine convergence for telescoping series by looking at the nth partial sum. But it's pretty clear that this is not a telescoping series. So the only other test we have at this point is the integral test. And to apply this test, we need to think of the general term of our series as a function, f of n, which in this case is n times e to the negative n squared. And in order to use the integral test, recall that we need this function to be positive, continuous, and decreasing over the interval where we're taking our sum. Now for this function, it's the product of n and e to the negative n squared, which are both continuous functions, so the product is going to be continuous. And each of these functions are positive as long as the interval that we're working over is positive, which in this case it is, since we're summing from n equals 0 to infinity. So let's start by saying clearly this function f is positive and continuous on the interval where we're summing from 0 to infinity. Now, the last thing that we need to show is that this function is decreasing. And to show that a function is decreasing, we would show that its derivative is negative. So if we were to look at the derivative of this function, f prime of n, we're going to need to make use of the product and chain rules. So here the derivative of our first factor, n, is 1 times the second factor, e to the negative n squared. Then we add the first factor, n, times the derivative of e to the negative n squared, which by the chain rule is negative 2n e to the negative n squared. Now, if we factor out a e to the negative n squared from each term, we're left with 1 minus 2n squared. And as long as n is positive, that is over the interval from 0 to infinity, we see that this expression would be negative. 1 minus 2n squared is going to be negative over this interval. So we have now that f is decreasing on our interval 0 to infinity. So we've established that f is positive, continuous, and decreasing over our interval. And the next step to apply this integral test is to consider the improper integral of our function on the interval which we're taking the sum. So in this case, from 0 to infinity. So let us consider the improper integral from 0 to infinity of our function, which in this case is x e to the negative x squared. Here we're just replacing n by the variable x that we're a little more familiar with working with. Now, to evaluate an improper integral, we have to make use of a limit. So we would take the limit as t approaches infinity of the integral from 0 to t of x e to the negative x squared dx. Now, to find the antiderivative for this function, we could make use of a substitution. So here, if we choose u to be negative x squared, then du would be negative 2x dx, so that dx is du over negative 2x. So when we evaluate our antiderivative for this improper integral, well, we have the limit as t approaches infinity, and then our integral in terms of u is now e to the u du with a factor of negative 1/2 out in front. And then if we change our limits of integration from x values to u values, we have a lower limit of integration of 0. And when x is equal to t, then u is negative t squared. So we have the limit as t approaches infinity of negative 1/2 e to the u, evaluated from u equals 0 to negative t squared. So this gives us the limit as t approaches infinity of negative 1/2 of e to the negative t squared minus, when we plug in 0 for u, we have e to the 0 or 1. And in our last step, we take the limit as t approaches infinity, and we see that this first term, e to the negative t squared, as t gets larger, will approach 0. So here we're left with a negative 1/2 times negative 1, which is positive 1/2. So this improper integral converged. It converged to a value of 1/2. And the integral test says, well, if that improper integral converges, then so does the series. So here we can say the series converges by the integral test. So we've established that it converges. Now, one word of warning about applying the integral test is that just because the series converges, that does not mean that the sum of our series is the same as the value of this improper integral. Here we're told if one of these converges, then the other one must converge. However, the sum of our series is not going to be the same value as the improper integral. So here we know that it converges, but we are not able to find the sum of our series. So let's look at another one. In this next example, we have the sum from 1 to infinity of log n divided by n. And again, the first thing that we might try would be the test for divergence. Usually we always want to start by trying the test for divergence since it's so easy to apply. So in this example, we would be looking at the limit as n approaches infinity of natural log n divided by n, which would be the limit as n approaches infinity of, applying L'Hopital's rule, we could take the derivative of top and bottom, and the derivative of log n is 1 over n, divided by the derivative of our denominator is 1. So we have the limit as n approaches infinity of 1 over n, which is 0. So here we had a 0 limit for this limiting value, which means the test for divergence fails. So here, the test for divergence fails. So we have to apply some other test. And when we look at the general term of our series here, the natural log of n divided by n, we can see pretty quickly that it is not going to be telescoping, and it is not a geometric series. Therefore, the only other test we have right now is the integral test. So let's consider applying this integral test. Now, the first step in applying the integral test is to consider a function, f of n, which is given by the general term of our series. In this case, natural log of n divided by n. And we need to show that this function is positive, continuous, and decreasing over the interval that we're working on. So here, we have a ratio of 2 positive valued functions. We know natural log of n is always greater than 0 for n greater than 1. So we can say clearly f is positive. Now, I would claim that this is also clearly continuous over our interval. The only way that this function could be discontinuous is if we had division by 0 or a negative value for n, since we're taking the natural log of n. But over the interval that we're taking the sum on, that is from 1 to infinity, we have the natural log is defined, and we can't have division by 0. So this function is also clearly continuous on our interval from 1 to infinity. Now, the last thing that we need to show is that our function is decreasing over this interval. So to show that this is decreasing, let's look at the derivative of our function. So here, using the quotient rule, the derivative of our numerator would be 1 over n times the denominator, n, minus the numerator, which is natural log of n, divided by the derivative of our denominator, which is 1. And then the whole thing is divided by our denominator squared. So here we're left with 1 minus the natural log of n divided by n squared. And as long as n is greater than 1, here our numerator, 1 minus the natural log of n, will be negative. And then we're dividing by n squared, which is always a positive value. So that ratio is indeed less than 0. So we can say that our function f is decreasing on the interval from 1 to infinity. So we've established that our function is positive, continuous, and decreasing. Now, to apply the integral test, we're supposed to consider the improper integral of our function over the interval of interest. In this case, from 1 to infinity, we're looking at log x divided by x dx. And to evaluate an improper integral, we have to think about it in terms of a limit. Here we would be taking the limit as t approaches infinity of the integral from 1 to t of natural log of x over x dx. And to find our antiderivative of this function, we could make use of a substitution. So here we would let u equal the natural log of x, so that du is given by 1 over x dx. And so our integral in terms of u can be rewritten as follows. We still have the limit as t approaches infinity. Now the antiderivative, or the integral of this function, is now given by the integral of u du. And let's change our limits of integration from x values to u values. So here, our lower limit was x equal 1. So u, which is log of x, would be log of 1, or 0. And our upper limit, if x is equal to t, then u is given by natural log of x, which would be natural log of t. So we have the limit as t approaches infinity of, for our antiderivative, we have 1/2 of u squared evaluated from 0 to log t. So we have the limit as t approaches infinity of 1/2 of the natural log of t quantity squared minus, when we plug in 0 for u, we have 0. So in our last step, we would take the limit of this function as t approaches infinity, and we know that the natural log of t is an increasing function. So as t gets larger and larger, this inside function, natural log of t, is diverging towards infinity. So if we square that value, we have a value that is becoming unboundedly large. It's approaching infinity. So here, our improper integral diverges. It did not approach some real number. And if our improper integral diverges, the integral test says the series diverges. So here we can say the series diverges by the integral test. So in these last two examples, we saw that to apply the integral test takes a fair amount of work. We first have to introduce some function and explain why it's positive, continuous, and decreasing over our interval, and then we still have to evaluate the improper integral of that function. So this is why we usually leave the integral test as a last resort to determine convergence or divergence. We want to try to apply some easier test if we can. So let's look at some other ones. In this next part, part C, we have the sum from 1 to infinity of n over n plus 1. And as always, the first thing that we want to try for any series is the test for divergence. So here we would look at the limit as n approaches infinity of the ratio n over n plus 1. And as n becomes large, we have a ratio infinity over infinity. So applying L'Hopital's rule, we would have the limit as n approaches infinity. The derivative of our numerator is 1. Derivative of the denominator is 1. So we have the limit of a constant value 1, which is 1. Now, if we get a limiting value of anything other than 0, the test for divergence says that the series diverges. So here we can say the series diverges by the test for divergence. So in this example, part C, if we remember to apply the divergence test before trying any other test, we don't have to go through the work of applying the integral test. We get immediately that the series diverges by that easy test for divergence. So let's look at another one. In part D, we have the sum from 1 to infinity of 1 over n squared plus 1. And again, if we apply the test for divergence, taking the limit of 1 over n squared plus 1 as n approaches infinity, we get a limiting value of 0. So in this case, the test for divergence fails. We get no result about the convergence or divergence of this series. Now, in order to determine convergence or divergence here, well, the general term is 1 over n squared plus 1. So it's not a geometric series. It is not a telescoping series. So the only other method that we have is this integral test. And to apply this test, we need to introduce a function, f of n, given by 1 over n squared plus 1 in this case. And we need to explain that this function is positive, continuous, and decreasing. Now in this example, clearly our function is positive since we have 1 divided by n squared plus 1, and n squared is always positive. Then this ratio will be positive. It will be continuous over our interval, since my denominator, n squared plus 1, can never be equal to 0, and my numerator is always defined as a constant 1. And it's clearly decreasing. If I make the values of n larger, then my denominator, n squared plus 1, becomes larger, and the ratio of 1 over that constant becomes smaller. So in this example, there's not much work to show. We can say clearly this function f is positive, continuous, and decreasing on the interval that we're taking the sum over, in this case from 1 to infinity. So we can apply the integral test, which says that we are going to consider the improper integral over our interval from 1 to infinity of the function, in this case 1 over x squared plus 1 with respect to x. And to evaluate any improper integral, we've got to make use of a limit. So here we would be taking the limit as t approaches infinity of the integral from 1 to t of 1 over x squared plus 1 dx. Now the antiderivative of 1 over x squared plus 1 is arctangent. So we have arctangent of x evaluated from 1 to t. So we now have the limit as t approaches infinity of arctangent of t minus, when we plug in 1, we have arctangent of 1, which is pi over 4. And in our last step, we're evaluating the limit as t approaches infinity. So the limiting value of the arctangent function as t becomes infinitely large is pi over 2. Remember that function has a horizontal asymptote at positive and negative pi over 2. So as t approaches positive infinity, we get a limit of pi over 2 minus our constant value of pi over 4, which leaves us pi over 4. So since our improper integral is converging to some real number, the integral test says that the series must also converge. So here, the series converges by the integral test. So we're seeing a few examples where the integral test might be necessary to determine convergence or divergence of a series. And this integral test, combined with a result that we saw a little bit earlier in the course, will give us a new test for convergence of certain types of series. So let's start by defining a new type of series. Here, any series that has the form sum from 1 to infinity of 1 over n to the p power is called a p-series. And the special case of a p-series where p is equal to 1, that is the series 1 over n, summing from 1 to infinity, is what is called the harmonic series. Now recall that we had seen earlier in our course in the chapter 3 material on improper integrals, the improper integral 1 over x to the p evaluated from 1 to infinity will converge as long as p is greater than 1, and it will diverge if p is less than or equal to 1. That was called the p-test for improper integrals. So combining that result together with the integral test, we have the following result. a theorem known as the p-series test, which says that the p-series, 1 over n to the p power, taking the sum from 1 to infinity, will converge as long as the power p is greater than 1, and it will diverge if the power of p is less than or equal to 1. So the reason this holds is due to the integral test. We know that this p-series will converge if and only if the improper integral converges. And from our earlier work in chapter 3, we saw that this improper integral will converge only if p is greater than 1, and it diverges if p is less than or equal to 1. So we have the same result for convergence or divergence for the series itself. So let's look at some examples making use of the p-series test. In this next example, we're given some series, which is a p-series, and we're asked to determine whether it converges or diverges. So in part A, we have the sum from 2 to infinity of 5 over n times the square root of n. Now, it may not look like a p-series at first, but if we rewrite this as the sum from 2 to infinity of 5 over, we have n root n, which would be n to the 3/2 power. And although our numerator isn't the constant 1, well, any constant in a series we can always pull out in front of our sum. If I factor out a 5 from each term, I would have 5 times the sum of the terms 1 over n to the 3/2 power. So we see that this is now the general form of a p-series, where the power of p is equal to 3/2, which is greater than 1. So the p-series test says that this series will converge. We could say something along the following lines. Since the value of p is equal to 3/2, which is greater than 1, the series converges by the p-series test. So in part A, we have a series which is converging. Now in part B, we have the sum from 1 to infinity of 1 over the cubed root of n squared, which can be rewritten as the sum from 1 to infinity of 1 over n to the 2/3 power. Remember, the cubed root is the same as taking the 1/3 power, so n squared raised to the 1/3 gives us n to the 2/3. So this is a p-series where the power p is 2/3, which is less than 1. So the p-series test says that this series will diverge. So here we could say something along the lines of, since p is equal to 2/3, which is less than 1, the series diverges by the p-series test. All right. So in this last part, we've got the sum from 3 to infinity of 3n over the square root of n to the 7th. Now, it may not look like a p-series at first, but if we rewrite this a little bit, we have the sum from 3 to infinity of 3n divided by the square root of n to the 7th is the same as n to the 7/2 power. And now, simplifying this ratio, I have the sum from 3 to infinity of 3 divided by n to the 5/2 power. So here, my n to the first divided by n to the 7/2 would simplify to division by n to the 5/2. So this is a p-series where the power of p is 5/2, which is greater than 1. So we can say, since the power p is 5/2, which is greater than 1, the series converges by the p-series test. So in this first part of our section 5.3 material, we're discussing the integral test, which then ends up resulting in another test known as the p-series test, which allows us to establish convergence or divergence of the series by looking at an improper integral. And we had mentioned that one word of caution is just because the improper integral of our series converges to a certain value, the value of the series or the sum of our series might be different from the value of that improper integral. Now, if we were to have a series which converges by the integral test, how could we determine its sum? Or how could we approximate its sum? So that's what we're going to discuss in the second part of this section 5.3 material.